Hey y'all, welcome back. Today's lesson is a pretty important one. Not only is it going to lay the foundation for pretty much everything we're going to do this year, but it also connects what we've done in the first unit, which was study limits, to answer the question that we posed at the very beginning of the course, or one of the two questions, and that is how to find the slope of a curve. So this is one of the big questions that actually led to the development of calculus in the first place. There were two pretty influential mathematicians that more or less invented calculus kind of at the same time and independently. We've got Isaac Newton, which I'm sure you're familiar with, and then this other guy, Gottfried Leibniz, who also invented calculus around the same time. And they did so that they could answer some of these questions that just really had no answers up to this point. Or not that they didn't have answers, but that nobody around the whole world knew what they were. So one of these big problems is the tangent line problem. And what that problem basically is if you've got a curve that's not linear, so, we know how to find slope of a linear function pretty easily, but if it's not linear, how do we find the slope at any given point? So let's think about that. What we really want to do is, if we have a curve like this, is ultimately we want to find the slope at that point. And to find the slope at that point, we run into a little bit of a problem, right? Because we know how to find the slope between 2 points. All right, back in Algebra 1, or maybe even before, you learned about your good friend rise over run. But really what that meant was the change in y divided by the change in x. This Greek letter delta typically means change in mathematics. And you may have even had a more explicit formula for this, y2 minus y1 over x2 minus x1. So this formula is great, but the problem is that you need 2 points to actually find the slope. So if we just want to find the slope at a single point, well, this is kind of why we had the problem in the first place back in the 1600s. That is an issue. So one thing that we could do, though, is we could approximate what the slope is here. And the slope of this curve at this point is going to be equal to the slope of a line which is tangent to this point. Tangent meaning not the tangent from last year when you were studying trigonometry. That tangent has a slightly different definition. When I say tangent here, I'm talking about the geometry definition of tangent, which is that it just touches the curve in one point. So anyway, the slope of this line is going to be the same as the slope as the curve of the curve at that point. Now, still, it doesn't really help us in the big scheme of things, drawing this line, because while we still have that point, we'll call this C and f of C. So that point is C comma f of C. We don't have a second point out here, right? So that still, poses a little bit of an issue. But what we could do is we could estimate the slope by picking a point that's actually on the curve. So let's say I picked a second point somewhere out here, right? And I drew a line connecting C comma f of C to that second point. So let's draw a line here going through this point. Now we can see pretty obviously that these two lines do not have the same slope, right? You can see that, but you can see that, they're not the same, but it's a reasonable approximation. It's not great, but it's not terrible either. Now we want to be able to refer to this other point that we're picking here, up here. And so what we're going to say is that if we're going to use this slope formula and we're going to use that other point, what we're going to say is that the distance between C and that other point, so let me just change colors here. The distance from here to here, where the x value of the secondary point is what I'm going to call the change in x, right? x2 minus x1, or delta x. So this point over here, this x value of this other point I've chosen, is c plus that delta x, plus that change in x. The y value of that point is going to be whatever the value of the function is at that c plus delta x. Okay, so long story short, we can calculate this particular, you can calculate the slope here, right, between c and c plus delta x. But let me pull on over here and kind of clean up this diagram a little bit. So we're going from this point, which is c comma f of c, to this other point, which we're calling, now here's c. This point would be c plus the change in x. So the x value here is c plus the change in x, comma, we lost you. There we go. Comma, the value of the function at that point. So this first point would be f of c, but the second point would be f of c plus delta x. Okay, so we've got these 2 points, and we want to find the slope in between these 2 points. So we're just going to substitute in these 2 values, the c, f of c, that could be like our 0.1, and our 0.2 could be this c plus delta x, comma, f of c plus delta x. And we could just plug that into our old school slope formula. So here, let's find the slope. y2, that's going to be our f of c plus delta x, minus y1, which would be f of c, divided by x2, which would be c plus delta x, minus x1, which would be c. Now we can simplify this just a tad here. Notice that c minus c will equal 0. So we can simplify this expression to say f of c plus delta x, or the change in x, minus f of c, all divided by delta x. This formula is really just the slope formula, but written in terms of just a single value, which is this single point c. Everything else, I guess, also in terms of delta x as well. But really, that's just the change that, how far away is that c value from the x value of the second point. So we could calculate the slope. We don't have any numbers here, so we're just going to leave it at that. But what you might be thinking at this point is like, hey, this is kind of a crappy approximation here, right? Like if this is my tangent line that I'm trying to approximate, the slope of that other line, like it's somewhat close, but it's not very close. So you might be thinking, okay, well, how can we get a better approximation? Okay, we're still going to think about this formula. Okay, we'll come back to that. But let's try something a little different. Okay, the slope that we're really interested in is the slope of this tangent line, right? That will be the same as the slope of the curve at that point. And if we pick that point that we just did somewhere out here, we get a line that looks like this, right? However, if we bring these 2 points closer and closer together, so like if my delta x, which is here, gets a little smaller, change the color there. If I pick a point that's like slightly closer, here's the tangent line, here's the line between those 2 points. It's not super obvious here. I could have probably chosen a better curve for this, but the slope of that green line, now that we've made the delta x a little smaller, is going to be closer, a better approximation than the original line. So, this is going to be better or closer than this. Right? And if we continue that process and try to make delta x as small as possible, so let's make it a little bit smaller, right? Let's pick a value that's a little bit closer to the original point. somewhere here. Now I think we're going to start to see that slope approximation is getting a lot better, right? Like if you're examining the angle between these two lines, that angle is getting smaller and smaller. That slope approximation is getting better and better. Oops. Kind of deleted my tangent line there. Okay, so this is delta x in the case where we're like pretty close, but really you want to get as close as you can, right? Like if I put these 2 points like right next to each other and make my delta x very small, now my tangent line is going to look very similar. Okay, let me try to draw that again. The slope of the tangent line, which is going to be something like this, really trying hard to hit that, is going to be pretty close to this. We can say it's still not like totally there, but it's even better. And if we look at all these different approximations, hopefully what you're seeing is that as delta x becomes smaller, the closer our slope approximation is going to be. And this is where limits come in, because limits allow us to talk about the infinitesimal. What we really want is for delta x to not be 0, but be as close to 0 as it can possibly be. In other words, we want to create a limit where delta x is approaching 0. So let's go ahead and rewrite that slope formula, but with the idea that, hey, that delta x, we don't want it to be big, we want it to be small. So slope will equal the limit as delta x approaches 0, right? We want to get that delta x to be as small as possible in that slope formula. Okay, I'm going to put x here instead of c because, you could call that c, but I want this slope formula to work at any point rather than a specific point. I'll come back to that idea in just a second here. But we've got the f of x plus delta x minus f of x all over delta x. Now, this can get a little confusing because you've got the x and the delta x. So oftentimes what you'll see, and I'll just kind of make this transition just here and now, although you may see this in some textbooks written like this, but oftentimes we're going to let the letter h be that delta x. Okay, so we're going to rewrite this limit as the limit as h approaches 0. And then it's the same formula. We're just kind of cleaning it up a little bit so that we don't have to write delta x, all that over and over again. This will just make the algebra look a little nicer. Okay, so here is our slope formula. This formula will give you an equation that describes the slope of any continuous function. So the limit's got to exist. There's some nuances there, but for now we'll just kind of take it for what it is. Now, going back to the original slope form, the way we wrote slope before, notice here we had like a specific value c. And so if you're looking for like the limit at a specific x value, so at x equals c, basically all you'll do is just substitute c into x. So you'd have the exact same slope formula here. It just replace that x with c. Now, for today, this form, kind of thinking about it like this is not going to be terribly useful. I think it's a lot easier to just find the equation for the slope using this formula. And then if you want to know what the slope is at like x equals 5, is just to go ahead and plug in 5 after you've already computed the slope. That being said, I have seen some AP questions where they'll give you an expression that looks like this with like a number here, like let's say 9, or even maybe an expression, and you'd be required to, basically understand that this is just talking about the slope at a specific point c for a function f of x. Okay, so We're still, I haven't done any examples here yet, but I really just want to take it slow and talk about the connection between limits and slope. Okay, one of the overarching questions of this whole course is how do we find the slope of a curve? And so this is actually the answer. Now, you're going to see today that the algebra gets a little crazy. Okay, there's going to be some pretty intense algebra. It'll be similar to some of the limit problems we solved in the last unit, but just bear with me for today. Just understand that this is going to be kind of the peak in terms of the difficulty of the algebra. And from here on out, it's going to get easier, I promise you, especially starting with our lesson 2-2 on the power rule. Okay, so let's look at some examples to see how we can find the slope. This first one says use the limit definition of slope to find the slope of f of x equals 6x plus 5. Now, you're hopefully thinking, hey, wait a minute. This is just a y equals mx plus b equation. I know what the slope is. The slope is constant. It's 6. And yeah, that is totally true. The slope here is 6. Now, that being said, I do want you to find that using the limit definition to more or less prove that it's 6. So we already know what the answer is going to be, but let's make sure the algebra checks out. And the reason why we're doing this on an easy one is so that when we get to the harder ones, you can hopefully have yourself convinced that this is giving you what you want it to give you. So let's do the limit definition here. We want to say the limit as delta x, or I'm going to call it h, approaches 0. So we're basically like moving the 2 points as close together as possible. My y2 is going to be f of x plus h. Now, before I write that, let me go ahead and erase that actually. So this f of x is given, right? This is f of x. F of x plus h is going to be the expression we get when we substitute x plus h for x. So that would be 6 times x plus h plus 5. So that is the f of x plus h. That is what we see up here. Okay, so let's go ahead and write that. 6. Oh, that's a highlighter. Let's go back to the pen here. So we've got 6 times x plus h plus 5. So that's the f of x plus h minus, maybe I'll put that in brackets just to make it more obvious, minus f of x, right? This is the second part of the formula. That's your y1 essentially. It's the original point that we're kind of interested in here. Where are we? F of x is 6x plus 5, all divided by h. So we need to calculate this limit. Move this over here just a little bit, just so it doesn't get too cluttered here. Okay, so this is where the algebra comes in, because what we need to do is we need to simplify that numerator, and then hopefully we get to remove a removable discontinuity or cancel out that h. We can't use direct substitution up front because we can't divide by 0. But we've already gotten a lot of practice in as far as how to simplify and get these to cancel out in our limits unit. So hopefully, a little bit of this algebra is a review. So I'm going to first distribute the 6, and that'll give me 6x plus 6h plus 5. And then I'll distribute. Make sure that you take, this is gonna catch a lot of y'all off guard, as you're gonna forget to make that both of these terms negative. Just make sure you're distributing that negative. Okay, so cleaned it up a little bit. And what you should be noticing at this point is that we have quite a few terms that are going to cancel out. Okay, we've got 6x minus 6x, right? 6x minus 6x, that's going to be 0. So those are going to cancel each other out. And we also have 5 minus 5. And you understand that that equals 0 also. We then can see that all we have here in this expression is 6h over h. Maybe it'd be worth like rewriting this, so I'm not doing too much at once. Right, and at this point we can see that these h's will reduce to 1, and we know for sure that works because h isn't 0. H is approaching 0, but it's not actually getting there. So since we're not actually dividing by 0, it is safe to cancel those out or reduce it to 1. So what we have is the limit as h approaches 0 of just the function 6. Right? There's nothing to plug in here, no direct substitution, so it's just going to be 6. So the slope of 6x plus 5 is exactly what we thought it was going to be, 6. Now you might be wondering, like, this is such a roundabout way of finding the slope, especially for a linear function. Why are we doing so much work when I could just look at that leading coefficient and give you the answer? Well, not all these are going to be linear. In fact, most of them will not be. So let's say we have a nonlinear function like this quadratic here, x squared minus 1. So f of x is x squared minus 1. F of x plus h would be x plus h squared minus 1. So what this is asking us to do is find an expression to find the slope and then figure out what the slope is when x equals 2. Now, you don't necessarily need to graph this, but just to get an idea of what's happening, this is the parent linear function shifted down 1 unit. Okay, so this is at -1, this is at 1, we got 2 comma, what would that be, 3, and so forth. And hopefully you see that the slope is not constant here. At the vertex, the slope's going to be 0. To the right of the vertex, the slope is positive, but it's kind of changing. On the left, it's negative. Again, it's changing. So it's different everywhere. And so what that limit definition is going to give us is an expression in terms of x. So basically what we're doing is we're coming up with an equation that will describe the slope at any x value. And then once we have that equation, we can go ahead and just pop 2 in and figure out the slope there. We can see from this really crummy sketch here that it's definitely going to be positive, probably more than 1. A slope of 1 is 45 degrees. So it looks like it's a little bit more slope than that, maybe a lot. But that should be kind of your guiding number here. We're expecting a slope to be bigger than 1 when x is 2. All right, so let's dig into the algebra here. We've got the limit as h approaches 0 of f of x plus h, so that's the x plus h squared minus 1. That's my f of x plus h, minus f of x, which is x squared minus 1, all divided by h. So just like with the last one, we can't just use direct substitution right away. We've got to manipulate this, get some stuff to cancel out, and hopefully we can plug it in at the very end. So let's multiply some of this out. So x plus h squared is going to be x squared plus 2xh plus h squared. Okay, that's just this piece right here. Then I have a minus 1 right after that. And then I've got minus x squared minus 1. Again, make sure that you distribute that -1 to both of these terms. So it's negative x squared plus 1. Now, once you've multiplied everything out, this is where you're going to start looking for things to cancel out. And these are going to be set up so like most of the time, they're going to have a lot cancel out. So like here, I've got x squared minus x squared. Those are going to go away. Here I've got 1 minus 1. Those go away. And actually, that's about it. Still haven't got rid of that h yet. But if you look closely, what we have left in the numerator is 2xh plus h squared. Both of those terms have an h. So we can factor out an h as though it's a greatest common factor. Now that we've factored out the h, we can reduce h over h to 1. And then we've got just, well, nice little linear function here. We got 2x plus h. Now, as h goes to 0, this expression is going to go to 2x plus 0. So this is going to be 2x plus 0, which is 2x. So 2x is going to describe the slope of x squared minus 1. So 2x is the slope of x squared minus 1. Yeah. And so basically what that means is if we want a slope when x is 2, well, we could just throw that into our slope equation. So our follow-up statement here, kind of wish I had a little bit more space here, but I'll say the slope of x squared minus 1, or I'll say just y equals x squared minus 1, at x equals 2 is 4. Okay, 2 times 2 is 4. Now, as you can see, like with this problem, slope's not going to be a constant value when the function isn't linear, right? Whenever we go through this limit process to find the slope, we're going to, except for linear functions, end up with an expression in terms of x because the slope is always changing. And so depending on x, we're going to have a different slope. So this equation that we're coming up with to describe the slope at any point is called the derivative of f. So when I use the word derivative, what I mean is slope, okay? But this derivative is just like the name of the function that describes the slope. And there's a couple different ways that we could notate this. That Leibniz guy that we talked about before who invented calculus, not alongside Newton, but sort of parallel to him, used this notation, f prime x. Okay, you can call this f prime x or just the derivative of f of x. Yeah, either way is fine. Usually I'll just say f prime because it's way easier to say. So just a lot less wordy. We also have something called Lagrange notation, which is dy over dx. Or sometimes you'll see it as d over dx with the function in like brackets or just sometimes right next to it. Now, these are both basically saying the same thing. Dy over dx, what this really means is the derivative of y, or in this case, the derivative of f of x with respect to x. So the derivative of y with respect to x. Now, I know you're wondering this. What did Newton use? He was the other guy that invented it. Why aren't we using his notation? Nah, you're not thinking about that at all. His notation looked like this. Y with a little dot. Yeah, I'll have to look into why we don't use that anymore, but just a little fun fact. That's Newton's notation, but we're not going to use that. Poor Newton. Okay, so this next question says, if g is t divided by t plus 1, find g prime. Okay, this means find the slope of g of t. That's what it's asking. Okay, find the slope or the derivative of g of t. So we're going to use our limit definition of slope. And this is going to be another one, just to warn you, buckle up for some wild algebra here. We're going to have to deal with some fraction action. Let's get started. The limit as h approaches 0 of something over h, right? And it's f of x plus h over f of x. So in this case, we don't have f of x, we have g of t. I'm going to write this out to the side. You know what? Let's clean this up a little bit. Let's put a little line here. There we go. So if if g of t is t over t plus 1, then g of t plus h is t plus h over t plus h plus 1. All right, so that t plus h over t plus h plus 1, that's our g of t plus h. So that's going to go first. So t plus h over t plus h plus 1 minus g of t, which we can see above, is t over t plus 1. Now, we solved quite a few limits that were set up kind of similar to this in the last unit. We didn't really know why. They seem kind of random, but I hope you can start to see the value in this. This is going to be a problem where we got to find a common denominator, try to rewrite this fraction, hopefully cancel out an h at the very end. So let's find our common denominators. We're going to multiply this fraction by t plus h plus 1 over t plus h plus 1, right? It's the denominator of the other fraction. And then we're going to multiply this one by t plus 1 over t plus 1. I told you all this is going to get messy. Hopefully you did not think I was kidding. All right, so we got the limit as h approaches 0 of t plus 1 times t plus h minus t times t plus h plus 1 all over t plus 1 times t plus h plus 1 all over h. Now, just to kind of clean this up just a hair here, I hate dealing with fractions and fractions. So I'm going to rewrite this. Instead of saying divided by h, I'm going to write this as times 1 over h. It's just the definition of division anyway. So I'm just going to rewrite it like that to make it a little bit easier. All right, so let's go ahead and do the multiplication in the numerator here. And hopefully we see some stuff cancel out. So t plus t, t times t is t squared. T times h is going to be just, well, ht, plus 1 times t, plus 1 times h. So that was just foiling this first part. Yeah. Minus t squared minus ht minus t all over t plus 1 times t plus h plus 1 times h. Now recall that when we did this in the last unit, we normally did not try to simplify that other factor product or that other product. So we're going to leave that denominator as it is. If we have to multiply it together, we will, but let's hope that doesn't happen. All right, we're on the hunt for terms that cancel out. So we've got t squared, we've got negative t. Those are going to reduce to 0. We've got ht minus ht. Those are going to go away. And then we've got t minus t. That's all 0. So this is going to clean up pretty quickly here. We've got the limit as h approaches 0 of h over t plus 1 times t plus h plus 1 times h. The h divided by h is going to be 1. And so now we've got the limit as h approaches 0 of 1 over t plus 1 times t plus h plus 1. And now that we've removed the removable discontinuity, that h that was causing all the problems, at this point we can just go ahead and plug in 0 for h. So 1 over t plus 1 times t plus 1. And this is the derivative of g. You could also write that as 1 over t plus 1 squared. You don't necessarily need to do that, but you could. All right, so this is g prime of t. So what this equation does, remember, we're finding the slope function. We are finding an equation that describes the slope of the original function at any, in this case, t value. Let's do another one that gets a little nasty. Okay, we want to find the derivative. Notice the change in notation here. Before I called it g prime, now I'm calling d dx. It's still the same idea, though. We're just finding the derivative. Just two different notations that mean the same thing. So let's start out by figuring out our f of x and our g of x. I'm sorry, f of x and f of x plus c. F plus h. Wow, okay. So my f of x is going to be 5x minus 8. My f of x plus h is going to be the square root of 5 times x plus h minus 8. Okay, let's get started finding our slope. The limit as h approaches 0 of f of x plus h, so that's the square root of 5 times x plus h minus 8 minus f of x, so that would be minus the square root of 5x minus 8, all divided by h. So we want to compute this limit. We've seen problems like this before in our last unit where we had a couple rational square root functions in there. And so the way that we dealt with this kind of limit to hopefully close the hole or remove the removable discontinuity is to multiply both the numerator and the denominator by the conjugate of that irrational expression. So here we go. I'm going to multiply both the numerator and the denominator here by the square root of 5 times x plus h minus 8 plus the square root of 5x minus 8. Make sure you're switching this sign. That's what makes it the conjugate, is that one's plus, one's minus here. We're also going to multiply the denominator by that, but just like the last problem, we're not going to actually multiply that denominator out because we're going to hope that that h cancels and we can use direct substitution. All right, so multiplying the numerator, we've dealt with this before when we multiply conjugates with these square roots. What happens is the square roots basically go away because the square root of x squared is just x. And the two middle terms will cancel out, and then we'll have the last term, which is just going to be 5x minus 8. So this is going to equal the limit as h approaches 0 of that first square root squared, so just 5 times x plus h minus 8, minus the second thing squared, which is just going to be 5x minus 8. So here's the first expression. Here's the second one over h. Not just h, though. We got more going on in that denominator. H times the square root of 5 times x plus h minus 8, should be all underneath that same square root, plus the square root of 5x minus 8. Looks like I left off a little parenthesis right there. And I did it again down here. All right. Okay. So now we need to simplify that numerator. So distributing the 5 is going to give me 5x plus 5h minus 8. And then we have minus 5x plus 8. All divided by, I'm just going to leave that denominator the way it is. Really got to pay close attention to detail here. There's so much stuff going on in this expression. If you miswrite one little thing, you can throw the whole thing off. So just take your time. Write one term at a time. Let's look back at that numerator. We got 5x minus 5x. Those are going to sum to 0. And then we've got 8 minus 8, which sums to 0. And then you can see that we've got this h over h, which reduces to 1. Right? This will reduce to 1. So what we're left with is the limit as h approaches 0 of 5 all over the square root of 5 times x plus h minus 8 plus the square root of 5x minus 8. We've gotten rid of that removable discontinuity. yeah, we've gotten that h we canceled out in the previous term. So I'm kind of thinking we can go ahead and try our direct substitution now. Let's go ahead and do that. We're going to plug in 0 for h. That's going to give me 5 over the square root of 5x minus 8, right, because that h is 0, plus 5x minus 8. And there we go. This is the derivative. This is d over dx of root 5x minus 8. You could simplify this a step further, since both of those square roots in the denominator are the same, and just write it as 2 times the square root. Not totally necessary, but you could do that. All right, man, I was not kidding about the algebra being intense today, huh? Yeah, we're not messing around. Okay, we've got one more derivative problem, and then I want to just talk briefly about some cases that you might encounter where the derivative doesn't exist. And we're going to spend a lot more time talking about that as the unit progresses, but I just wanted to give you a little preview of what's coming up. So let's do one more limit derivative here. Now, if f of x is 3x squared plus 5x minus 8, then that means that f of x plus h is going to be 3 times x plus h squared plus 5 times x plus h minus 8. So yeah, this is going to just, maybe take a breather here. Maybe pause the video, take a little brain break, because I want you totally locked in for this problem. All right, let's go. Find the derivative. I'm going to call it f prime. I just kind of prefer Leibniz notation. I don't know. I just thought I like it better, but whatever. Okay, so f prime equals the limit as h approaches 0 of f of x plus h. So here's f of x plus h minus f of x all over h. And now we want to simplify that numerator. So squaring out the x plus h is going to give me x squared plus 2xh plus h squared. But then I need to go ahead and multiply that by 3. So I get 3x squared plus 3 times 2 is 6xh plus 3h squared. So this is just that first 3x plus h squared. Then I can distribute this 5 as well. So that's going to be plus 5x plus 5h. And then I have a minus 8. And then I'm going to distribute that negative. So minus 3x squared minus 5x plus 8 all over h. Whew. All right, let's see what we can get to cancel. See a 3x squared and a minus 3x squared. That's nice. And then we've got a 5x and a minus 5x. We've got a plus and minus 8. And that's it. So what we're left with is 6xh plus 3h squared plus 5h all over h. Notice how each term in the numerator has an h. So we can factor out that h as a greatest common factor. Yeah, there we go. Now we've got that h. We can remove the removable discontinuity. We can reduce this h to 1. And so we're going to have the limit as h approaches 0 of 6x plus 3h plus 5. And now we can just go ahead and use direct substitution and plug in this 0 into h. So this is going to equal 6x plus 5. So this is the derivative. This is what f prime of x is. That equation is going to describe the slope of f of x for any x. So part B says find the slope at these different, x values. So here we're just going to plug in the numbers into the derivative equation. So f prime of 0 would be 6 times 0 plus 5, which is just 5. F prime 1, which is the slope when x is 1, is 6 times 1 plus 5, which would be 11. And then f prime negative 2 would be the slope when x is negative 2, which would be 6 times negative 2 plus 5. That'd be negative 12, and 5 is going to be negative 7. Part C says write the equation of the line tangent to the graph at x equals 2. So in order to do this, and this is kind of a non-negotiable, you are going to need to be familiar with the point slope form of an equation. You got to commit this to memory. There's not really any way around it. You've been working with it since Algebra 1, but now it's really going to come back with a vengeance here. Now, to use this point slope form, we need a point and a slope. Now, the point is going to be at x equals 2, comma, we need the y value. So what we need is, like, what's f of 2? We need to plug in 2 back into the original function up here. Okay, so 2 squared would be 4, times 3 is 12, plus 10 is 22, minus 8 is 14. So the point's going to be at 2 comma 14. The slope is going to be the value of the derivative when x is 2. All right, we already found the slope equation was 6x plus 5. Right, see it over here. This is the slope equation. And so if we want the slope when x is 2, we're going to plug in 2. So we get 6 times 2 is 12, plus 5 is 17. So once we have our point and our slope, we can just throw all that into our point slope formula. So y minus 14 equals the slope, which is 17, times x minus 2. There's our equation for the line that's tangent to the function at x equals 2. So going back to the very beginning here, this isn't that particular curve, but that equation that we just found would be like that red line that we were trying to figure out earlier. One last thing I want to talk to y'all about is starting to get an idea of when would the slope not exist. And so there's a couple of different reasons why the slope might not exist. One place, you can kind of look at this graph and make some predictions. But I think probably the most obvious place it doesn't exist is where the function is not defined to begin with, where you have a discontinuity. In this case, we've got like a vertical asymptote occurring at x equals 4. And so we would say that the slope of f when x is 4 does not exist. Okay, and that's because at that point, f is not continuous. Let's be clear here, at x equals 4. Okay, so that's one, if you have a vertical asymptote or even a hole, the derivative is not going to exist there. The function's got to be defined. Okay. Now, another place that you might not see, that might not stick out at you, but right at -6, we have what I'm going to call a sharp corner. Okay, so f prime of -6 is not going to exist either, because of what, for now, I'll just call a sharp corner, or sharp turn. And basically, if you have like a V-looking thing in your graph where the slope suddenly changes, it doesn't change gradually, but where the slope changes like instantaneously, like without being very curved at all, then we're going to say the slope doesn't exist there. How would you draw a line tangent to a point like this? It's going to be like that or like that or like that. It's really unclear. And so we're going to say for now that it doesn't exist, but we're going to investigate go into detail a little bit more later in the unit. So yeah, it's not going to exist at -6. Two other places that kind of fall in the same category here are going to be at -9 and 9. And what both of these locations have in common is that they're endpoints to the graph. So in order for you to calculate the slope at a point, the function must continue on from the left and to the right. It can't be an endpoint. Okay, so the slope here is not going to exist because they are endpoints. Okay, so we have like a discontinuity, which might cause the slope to not exist. We've got a sharp corner, which will cause it not to exist. Endpoints cause the derivative to not exist. And one other subtle little thing that might happen, it's like take a look at what's happening at -1. If I try to draw a tangent line here, it's going to be vertical. This is something that we will also investigate down the line. But if f of x has a vertical tangent line at some, in this case at -1, then we say that that slope doesn't exist either. Okay, so this slope does not exist because f of x has a vertical tangent line. Okay, so in today's lesson, we talked about what is slope, right? How do we find slope of a curve? We're going to find it using this limit definition. That's where the limits come into play. And what we did is we looked at several different equations and found their slope formula, which we're now going to call the derivative. So when we find that derivative, we can find the slope at any given point. And so that's kind of what we're doing down the line here, is finding the slope at different locations. We're able to now write an equation of the line that's tangent to the curve. And we're starting to investigate when the derivative may not exist. And again, we'll go into more detail of that down the line. But this has been a pretty hefty lesson, but I really want to encourage you to hang in there. I promise you the algebra is going to become easier as we move forward. But just do the best you can, just keep practicing these limits and it will come together. Y'all, thanks for watching, and I'll see you next time.